Today we will discuss about the FIR filter design. So FIR filter design. Now this is the this equation we have already discussed when I introduced the concept of digital filters. The point is that the design of a digital filter is the task of determining a transfer function, which is a rational function of z to the power minus 1. So what is the rational function? A rational function will take the form of this expression a0 plus a1 z to the power minus 1 plus a2 z to the power minus 2 plus a3 z to the power minus 3 and so on. And in the denominator you will have 1 here, 1 plus b1 z to the power minus 1 b2 z to the power minus 2, right? This expression is in the case of an IIR filter, and in the case of an IIR filter, but the other expression a0 plus a1 z to the power minus 1 plus a2 z to the power minus 2 plus a3 z to the power minus 3. This is the case of a non-recursive filter. So these are the examples of general expression that you will have to find out when you are designing a digital filter. All right. Then, how do we specify a filter? I am taking the example of a low-pass filter, right? Now, how do you specify? What are the various specifications of a low-pass filter? Now, if you look here, this point is 1. 1 actually corresponds to 0 dB. Either you can say 0 dB or 1. That means 1 is gain. This is normalized gain. All right. So that is why the value is 1 here. So this is 0 dB and this is normalized gain. Now, how much ripple is there? Now, from if you see the pass band up to this point, this is the pass band of the filter. That means along x-axis is the frequency. I'm particularly talking about digital filters, so I will talk about digital frequency. But a separate axis I have drawn, which actually equates the analog frequency with the digital frequency. But that's not important. At present, along the x-axis is the digital frequency, along the y-axis is the magnitude response of the filter. Now, if you look, this is the gain 1 or 0 dB. Now, how much ripple is present in the pass band, right? So let's say that ripple is delta 1. So above that 0.1 here will be 1 plus delta 1, and below will be 1 minus delta 1. So this is the 1 plus delta 1 to 1 minus delta 1 will actually tell you how much ripple is present in the pass band. Now, when the filter, because it's a low pass filter, when the filter response goes from the pass band towards when the attenuation becomes very high and it goes towards the stop band, and at this point, corresponding to this point, if you are able to see, you see here delta 2. Delta 2 is the stop band attenuation given. Delta 2 is the stop band attenuation, beyond which we will say that this is the stop band. And these ripples present in the stop band we call these as the ripples, stop band ripples. All right. Now, omega L is the frequency corresponding to 1 minus delta 1. Omega U corresponds to the stop band attenuation. These are the specifications you need to specify when you design a filter. All right. And from when the filter frequency response is making a transition from the pass band to the pass band to the stop band, then that the band within which the transition is taking place, that band is known as the transition band. Okay. We will design filters, then you will be more clear about the specifications. All right. Now the goal of the design is to determine a transfer function. As I already said, we have to determine a transfer function. How we have to determine a transfer function? We will be given with specifications of a filter. For example, if I ask you to design a low pass filter which should allow 0 hertz to, let's say, 20 kilohertz of frequencies to pass through it, and rest of the frequencies it blocks. So that means I have given you the specification. All right, and I will also specify how much passband ripple I require in the passband. What is from where I would like to start the stop band. That means I will be giving you the stop band attenuation. So these specifications I will give you, and based on the specification, I have to determine the transfer function of the filter so that its amplitude characteristic satisfies the condition that the magnitude response is within 1 minus delta 1 and 1 plus delta 1. And this is for the stop band attenuation also, that magnitude response is less than delta 2 for the stop band, right? The major thing is that I have to design a transfer function. Now let us see. This slide actually tells you the ideal characteristics of low pass filter. So this is a low pass filter. That means low frequencies will be allowed to pass through the filter and higher frequencies will be stopped. This is the second graph, is the example of a high pass filter. The third example is for a band pass filter, that a certain band will be allowed to pass through it. Before the band and after the band, the frequencies will be rejected or stopped. And there is a requirement of band reject filters also, in which you have to reject a particular band, right? So rest every frequency will be passed through it, only that band will be stopped, that band will be rejected. So these are the ideal characteristics of filter. We want actually these types of characteristics, but practical cases there is no sudden fall from the pass band to the stop band. Actually, it takes some time. So these are the actual filter characteristics. So from coming from the pass band towards going towards the stop band, it takes a certain roll off. There is not a sharp edge, you know. So this is known as the roll off of the filter to go from the pass band to the stop band. All right. So these are what I mean to say is that practically you never achieve these type of filters, but you design filters so that you come as close as possible to the specifications and to the requirement. Okay. Now, in my today's lecture, I will discuss about the FIR filter design, and that too I will discuss the window method of designing FIR filters. But there are other methods also, frequency sampling optimization algorithm, which is basically the Ramez algorithm. So we will continue with these designs in the later classes. And the techniques for the IIR filter design are impulse invariant transformation, bilinear transformation, all these techniques we will discuss in our course, because that's the important part of that's the crux of this course, basically, to design filters. All right. But we will today start with the window method of designing FIR digital filters. Now, the question is that, let's say we have a signal, and that signal is a speech signal. So speech signal is coming, continuously the output is coming from some transducer, right? From some sensor or any transducer, the output is coming continuously. Now, the question is that we cannot analyze the input coming signal from -infinity to infinity. We have to truncate the signal, and we have to look the signal within a frame, because particularly in the case of speech signals are my job is not our job in this course is not to study about these speech signals, but still I am giving you an idea. Speech signals are quasi-stationary signals, meaning by for around 15 to 20 milliseconds, the speech signals remain the same. That's what I have written in my next slides. Vocal tract shape changes every 15 milliseconds. So there is a 15 millisecond period for which the signal throughout remains stationary. All right. Now, we have to look this signal. If we want to analyze the signal, we have to look the signal within this frame only. Frame 1, frame 2. That means we should be able to truncate the signal. Truncate the signal within this frame, right? The meaning of the truncation will be clear when I go to the next slide. So let's go to the next slides first. Now, what is the meaning of what I want actually is my Sn is the input signal. Now I want to analyze this signal. I cannot analyze this signal from -infinity to infinity. If its impulse response ranges from -infinity to infinity, so that is not possible to analyze this signal. I will discuss the reasons also. What I will do is I will apply a window, another function, window function, and I would like to see this signal only in this range. The window size, there will be a size of the window. I will apply that window, rather I will multiply the window with this speech signal. What is the window function? Window function is 0 beyond this width of the window. So if I multiply the window function with the speech signal, I will be able to see or analyze this signal only. All right. So that's what actually is the process of truncation. How do you do truncation? You have an input signal, you multiply it with a window function. So you will be able to see through that signal only within that window frame. All right. So that's actually the process of windowing or window. So what I do is my Yn is the output signal, Sn is the input signal. I multiply the input signal with a window function. All right. But this is in time domain. All right. This is in this time domain. The speech signal or any input signal is multiplied with the window function and you get an output function. This is in time domain. Multiplication is done in time domain. But when you analyze the signal in frequency domain, so naturally the multiplication becomes convolution in frequency domain. Because of this convolution, actually it introduces distortion in the signal. When window is applied, the frequency domain convolution causes distortion in this spectrum. It can be shown. I will explain how this, we will mathematically analyze that how this distortion comes. Now let us take the first window, right? First window is a rectangular window, meaning by I want to analyze the samples from 0 to capital N, let's say. From 0 to capital N, the sample values are all 1, but rest of the sample values are 0. So that's how I define this window function. What is my window function? Wn equal to 1 from 0 to capital N minus 1 and 0 otherwise. So this is my window function. Now let me try to analyze this window function only at present. If I take its Z transform, if I take the Z transform of Wn, I will get this series. All right, Wn Z to the power minus 1, I will get this series. So this is a GP series, I will get the sum also. Now if I want to take its frequency response, I will have to replace every Z with e to the power j omega. So I do that, I get W of omega. That means I get the frequency response of this function. Function is a rectangular window. All right. So this is my Fourier transform or the frequency response. Now I do some modifications in the expression because I want to calculate I want to know the magnitude response and the phase of this frequency response that I have obtained. So the procedure remains the same. Half of this exponent you take out from the numerator, half of the exponent you take out from the denominator also, and you will be left with this term e to the power minus j capital N minus 1 by 2 omega sine of, and you can use the Euler's formula to get sine of n omega by 2 divided by omega by 2, which is basically a sinc function. All right. Now, what is my angle? My angle is this minus capital N minus 1 by 2 omega. So this is my phase, and this part is my magnitude. We have been doing this in my previous class also, and how to get the magnitude and phase response. Now, if I plot the magnitude response, I get zeros at minus 2 pi by capital N and 2 pi by capital N. So this is my, and from minus 2 pi by capital N to 2 pi by capital N, this is my main lobe of the, what is this? This is the magnitude response. Magnitude response of what? Magnitude response of my window function. All right. Now, if you analyze the frequency response of this window function, you see here there exists a main lobe, and there are side lobes also present in the frequency response. These are known as ripples, which are basically the cause of distortion that the particular window introduces in the frequency spectrum. So I can do the variations in this main lobe. If my capital N increases the width of the main lobe, if capital N increases, that means capital N here, I take more number of samples in the window, I include more number of samples in the window, what will happen? It will increase the width of the main, if N increases, the width of the main lobe decreases, right? This width will decrease, but the peak amplitude of the side lobe grows in a manner such that area under the each lobe is constant. If I try to reduce the width of this main lobe, the side lobes peak will increase, so that the area under the curve remains the same. The major point that I want to mention here is that if you put a window function, why do you put a window function? Because I want to analyze my signal through this window only. Only within this range I want to look at the signal. I will multiply the window function with the input, but when I multiply and I use this window actually introduces smear. This is known as smear distortion in the signal because of this side lobes. How did we know? We analyzed it from the frequency spectrum of the window function. Clear? Now, what are the design methods? So first we will try to look at the design methods using the window method. We know that FIR filter, I'm particularly talking about FIR filters now, right? No, I'm not going to IIR filters, only FIR filters I'm talking. So FIR filters have linear response. We have looked at these equations already also. The phase is like this, and they are stable also. We know that. Now, this is very important. So two equations are there. We looked at these two equations earlier also. If we can prove if we can prove that the phase response looks like minus a omega or b minus a omega, then we can say that the FIR filter has linear phase characteristics. Now, that's very important. Please try to understand this. It can be shown. I am not going into the mathematical derivation of how do you get this relationship, but it can be shown that for condition 1, this is my condition, phi omega is equal to minus a omega. If I can put my phase of a system in this form, I know that it's a linear phase. It can be shown that for condition 1, above to be satisfied, right? The impulse response of the filter must have positive symmetry. That's very important. What is positive symmetry? Hn is equal to h of capital N minus 1. These are known as symmetric filters. All right. And these are also known as type 1 symmetric filters. where n denotes the filter length. What do you mean by filter length? Because we are applying a window, and through that window only we will be looking at these many samples only. So that's why this is filter length. So when first condition is to be satisfied, then the impulse response of the filter must have positive symmetry. Now, in order to satisfy the second condition, the impulse response of the filter has negative symmetry. That means Hn is equal to minus H n minus capital N minus n minus 1, right? Now, what is the meaning of positive symmetry? Let's say the value of capital N is 13, some odd value. Then what is the middle point of this? 6 is the middle point. That means, what is the meaning of symmetry? The meaning of symmetry is that how many values of Hn will be there? There will be 13 values, H0, H1, H2, H3, H1, H4 up to H12. So H0 up to H12. What is the middle value? Middle value is H6. The coefficients from H0 to H5 will be the same as the coefficients. That means H0 will be equal to H12. This will be equal to this, 2 will be equal to this point. This will be equal to this point. This corresponding to 4 will be equal to this 8, that means what is the center point? The center point is 6. The left of this center, all the coefficients will be same as the coefficients on the right of the symmetry line, right? We will see that how these are same. And if the n is even, in that case, between 5 and 6 there is a middle line from 0 to 5, and from 6 to 10 the coefficients will be same. All right, I will explain these things in detail in the coming slides. Let us now, what is the method of designing? So please try to understand what is the method of designing FIR filters using windows. Now you take any, okay, before I, all right, let me explain from this example only. You take any infinite impulse response filter. You will be given with any IIR filter response, any filter response which is infinite. To take an example, I can say that this is what? This is the ideal low pass filter. The frequency response is 1 from minus omega c, from 0 to omega c, let's say. Let's not consider the negative side. From 0 to omega c it is 1, and it is 0 for every other frequency. This is the ideal low pass filter. Now if I take the impulse response from here, how I will take the impulse response? I will have to take the inverse Fourier transform. If I take the inverse Fourier transform, this is my impulse response comes, which is HDN is equal to omega c by pi for n equal to 0. That means for n equal to 0, it is omega c by pi, and for n not equal to 0, it is sine of omega c n divided by pi n. The point that I'm trying to say is that the impulse response of this ideal filter is infinite. It is going from minus infinity to infinity, right? As we can see that Hn is infinite. This is one example. The procedure of designing the FIR filters will involve that you take any IIR filter. Here I am taking a low pass filter and I am calculating its impulse response. I found out that the impulse response is infinite, right? But for that matter, you take any system which has got infinite impulse response. Starting of the FIR filters will start from here, that you take impulse response of a filter or a system having infinite impulse response, right? So I take a low pass filter, I found out its impulse response, and when I checked the impulse response, I found that it is infinite. As we can see, Hn is infinite, hence we need to truncate the higher coefficients. That's what truncation process is. Because I cannot from minus infinity to infinity, I cannot look at every sample. I have to define a window within which I have to look for the samples. So that's what the design procedure is. To start with, let me come back to here. So the easiest way to obtain an FIR filter is to simply truncate the impulse response of an IIR filter. Take an IIR filter with infinite impulse response, truncate it. What is the process of truncation? You have to multiply it with a window function. Now, if HDN represents the impulse response of a desired IIR filter, HDN is the response of the IIR filter, then an FIR filter with impulse response HN can be obtained like this. What is HN? HN is the impulse response of the FIR filter, because from N1 to N2 only the response exists. So therefore HN is the impulse response of the FIR filter. HDN is the impulse response of the IIR filter, which is an infinite impulse response. Okay. Now, so what we are given with? We are given with HDN, which is infinite impulse response, and we have to get HN out of HDN. However, we need to get? We need to multiply HDN, which is infinite impulse response, with a window function. As an example, I am taking a rectangular window. There are other windows also. We will look at the other windows also, Hamming window, Hanning window. Yesterday there was one lab class with me. So I did the experiment also with the Blackman window, Hamming window, Hanning window. Though I could not complete here the theory in the theory class, but I did that experiment. This is the same. You can correlate that experiment with the theory part. What is HN? HN is the impulse response of the FIR filter. What is HDN? HDN is the impulse response of the infinite IIR filter. WN is the truncation. That means we are applying the truncation through this window. And as an example, I am using rectangular window. If I take the Fourier transform, because I am multiplying here, it will become convolution in the frequency domain. All right. Okay. So this is my frequency response of the HD omega. This is the window function. That's how the response will look like in the final filter type. So this is let's not go into, let's stay to the procedure only at present. So as an example of explaining how you can apply this procedure. What is the procedure? As I said, the procedure is to take the infinite impulse response, multiply it with a window function, you will get the FIR filter design. So this is an example in which I take the case of an ideal low pass filter. When I see the impulse response is infinite. Now I have to convert it to an FIR filter. How will I convert? I will, an ideal low pass filter has a frequency response characteristics like this. To get FIR filter, this is important. To get FIR filter, HDN. What is HDN? Impulse response of IIR filter. HDN is truncated to be defined only between minus n and n is equal to capital plus n. This is equivalent to multiplying Hn by Wn. What is my Wn? This is 1 from minus n to n, 0 otherwise. So this is the example of a rectangular window. I am multiplying the rectangular. I am multiplying the, am I audible? Let me pass. Am I audible, please? If somebody can respond. Hello? Okay, okay. Thank you. Thank you. Because my connection actually it got disconnected. But anyway, so this is my impulse response of the IIR filter. This is my window function. All right. So I have to multiply HDN with W to get the. Okay. So what I do is I multiply the low pass filter, IIR filter, IIR response, infinite impulse response, low pass filter with the window function. All right. And I get the FIR filter response, which is HN. Okay. Now, what are the other windows that I can use? The other windows can be Bartlett window. We need not to go into the derivations of these windows. We have to take the formula straight away. One is Bartlett window, Henning window, Hamming window. These are different windows with the different the shapes of these window functions will be different, right? And they will be giving a different response to the output of the FIR filter. We will discuss about these other windows maybe in the next class. But, and you see, impulse response, okay, let me, actually it broke now, so let me explain, let me try to make the case once again. This is the case for an ideal low pass filter for IIR, which is infinite impulse response. When I look at the impulse response, how do I get the impulse response? I will take the inverse Fourier transform and I will get the impulse response of this low pass filter. And when I look at it, it is infinite. I have to design an FIR filter. How will I design? I will use this window function. I will multiply with HDN, right, to get the HN. So that's what my procedure was. If you remember, if you look at the procedure, HN will be obtained by multiplying HDN, which is infinite, with this window function WN. Right. Now, okay, then to get an FIR filter, okay, this is clear. I have done this. So here, this HLP or HDN, this is the low pass infinite impulse response of the low pass filter multiplied with the WN, and we get the HN, which is the FIR filter response. So there is a phenomenon which is known as Gibbs phenomenon. In the rectangular window, if you look at the rectangular window, what is the shape of the rectangular window? The shape of, okay, let me just have the rectangular window once again. Okay, this is the shape of the rectangular window. From 0 to n minus 1 or capital N, you see here the amplitude is 1 and it very sharply falls down to 0. It is a very sharp edge. Going from 1 to 0, it is a very sharp edge. All right. Because of this sharp edge, what happens is there takes place a phenomenon which we call as the Gibbs phenomenon. Now, what is Gibbs phenomenon? The new H omega, that means this new. What is H omega? H omega will be the Fourier transform of HN. What is HN? HN is the impulse response of the FIR filter now. And H omega is the frequency response of the FIR filter. Now the new H omega will not be the same as the ideal H d omega, which is my starting case, which is for the infinite response, impulse response. Now Gibbs phenomena is raised by this truncation of HN, because this truncation process takes place. If you look at the graph, if I can, okay. Now this is the H omega. The dotted line is H d omega. All right, for the almost the ideal case. But when you multiply it with a rectangular window function, it overshoots. So if you look at the dotted line, this is quite a constant kind of characteristics. But if you look at the at the FIR filter response. So it takes a rise here, then falls, but falls very sharply as compared to the previous one, and it then again takes an overshoot, right, and comes back. So this is known as Gibbs phenomenon. Why this Gibbs phenomenon has occurred? Because of the rectangular window, there is a very sharp, there is an abrupt fall of the amplitude from 1 to 0. Because of this abrupt fall, this overshoot takes place. The overshoot can be reduced. Now this overshoot can be reduced by increasing m. If we can increase the size of the window, the overshoot can decrease, but the oscillation increases. So if you look at the FIR filter, which is a bold line, there are many oscillations as compared to the previous almost an ideal case. All right. So there are oscillations and there is overshooting takes place, and this is known as Gibbs phenomenon. But this happens with the case of rectangular window. Now scientists have worked on the windows and they designed many other windows where if you let me come back to the rectangular window again, where there is not this sharp fall. Okay, here it is an abrupt change from 1 to 0, but the scientists have come up with windows which rise smoothly and then fall smoothly also. And they have come up with different functions of these window functions, right? Where the smoothness of the window is taken care, so that there is no sharp fall from 1 to 0, which gives rise to Gibbs phenomenon. So come back. Okay. So these are the scientists. These are the window functions that the scientists have given. The procedure remains the same. The procedure is you have to take the infinite impulse response, you have to multiply the infinite impulse response, this window function, you will get the FIR filter. So this is the Bartlett window, Hanning window, this is Hamming window, all right. Blackman window, I did the practicals also yesterday with one of the groups, and this is Kaiser window. If you look at the shapes of these window functions, I will show you. Probably I don't have the slide at present with me, but I will next time I will come up with the shapes of these window functions, where you will see that there is not abrupt fall, rather there is a smooth change from the high value to the low values, and this will avoid to a great extent the Gibbs phenomenon. All right. Now I took the case of ideal low pass filter, right? So let us take the case for high pass filter, band pass filter, and band stop filter. What I did was I took the impulse response of a low pass filter. This is my low pass filter, but I will have to design other filters also. So this is the HD. The first formula is the impulse response of the high pass filter. The second is the case for band pass filter, and the third is the case for band stop filter, right? So these are the infinite impulse responses. Now let us take an example. Now in this example, determine the impulse response HDN. Why I need to determine HDN? Because I am giving H omega. H omega is what? H omega is the frequency response of the IIR filter. All right. So H omega is the frequency response of the IIR filter. I need to derive HDN from here. How can I derive? I will have to take the inverse Fourier transform. Let's look at this part first. So this is my HD omega. Okay, this is the procedure given. I will take an example. Okay, this is the solution. All right, this is the solution. This is HDN. HD omega is given to me. Let us look at this example first. Okay, let us look at this example. HD omega is given to be all right, HD omega is given to be 1 from 0 to pi by 3, and it is 0 from pi by 3 to pi. So let us take the inverse Fourier transform. I think this is the, oh yes, this is the same solution. I thought some other solution would have come. But anyway, so this is the inverse Fourier transform formula. This is 1 from 0 to pi by 3, right? Or minus pi to pi by 3 if you consider the negative side also. Because here the function is mod, mod is present here, so you will have to consider minus pi by 3 to pi by 3. All right, you change the limits of this integral from minus pi by 3 to pi by 3. You solve this integral. What you will get is you will get the impulse, infinite impulse response of this given filter. What is the given filter? This is my given filter. What is the impulse response? I have got this impulse response. 1 over pi sine n pi by 3 divided by n. And if I put the value of n to be 0, it will come out to be 1 by 3. For n not equal to 0, this will come out to be sine n pi by 3 n pi. So this is my IIR filter impulse response. But given was the frequency response of the IIR filter. Now, for a linear phase filter, now if we look at the okay, I have not done the solution, but anyway, for further examples, the solution is there. If you take I will talk about the symmetry and anti-symmetry. If you consider, now if you calculate the using the window function will be multiplying this HDN with 1, right? You will get HN. Now, right? So once you get HN, so HN will be equal to HDN into WN. My WN is actually 1 for the rectangular window. And what is the value of N I am choosing? I am choosing in the example probably. In the example, what I have to design is, first thing was determine the impulse response. So I found out HDN. The second part is to obtain a finite impulse response from HDN. A rectangular window size is given, which is n equal to 9. So, okay, I found out HDN. What was my HDN found? HDN was this. I took the inverse Fourier transform. I got this HDN. Now, I have to now apply a window. My window size is given to be 9. Capital N is given to be 9. What is small n? Small n, what is the, because for a linear, given is that for a linear phase filter, it has to be symmetric. When capital N is odd, then it is a case of type 1 symmetric filter, right? In that case, what is the symmetry point? Symmetry point will be 9 minus 1 by 2, 4. I calculate H0. How do I calculate H0? When HDN multiplied by WN. WN is 1 only. This is my HDN. So for n equal to 0, it is 1 by 3. So my H0 comes out to be 0.33. Right. For H1, how do I calculate H1? Because when it is multiplied by WN, which is 1, so it remains the same. So HN, so that means H1 will be calculated by using n, the value of n to be 1. And it comes out to be under root 3 by 2 pi. H2 comes out to be under root 3 by 4 pi. H3 comes out to be 0 and H4 comes out to be minus under root 3 by 8 pi. All right. Now, but there are, how many coefficients there are? There has to be 9 coefficients because capital N is given to be 9. Right. So in that case, what will happen is that we know we need not to we can calculate other coefficients also by putting the value of H5, H6, H7, and by putting the values of N to be 5, 6, 7, 8, right? But what we will do is, we know that the filter is symmetric filter. For capital N to be odd, the other 4 coefficients will be same. Now, if you look at, and what we need to do is that we have to shift the impulse response to the right by a factor of 4. That means H0 will become actually H4, right? H1 will actually become H5. So it is shifted by 4. All the these impulse response values are shifted by 4. This becomes H4, H5, 6, 7, and 8. So that's what is that's what happens here. You shift the values. H0 becomes H4, H1 becomes H5, 6, 7, and 8. And what does the symmetry suggest? H8 will be equal to H0. I think time is up, but I will come back with this example tomorrow also. All right. I will explain the design of FIR filters. I will again come back with this example to explain how the FIR filters are designed. And I will take some more examples also because I have a lot of examples using different windows. So I will explain, everything will be clear of designing the FIR filter. I will start with the example once again and explain you the procedure and you will get the answer. For the
Excuse me sir.
please.
Sir PPT provide कर सकते हो इसकी?
ये PPT मैंने already upload कर दी है. All PPTs are on LMS. This is lecture 12 already uploaded on LMS.
Okay sir, thank you.
Okay, but I will come back with the same example once again and other examples also. All right. Thank you. All PPTs are available. Thank you so much. I will come back in the next lecture.